did not register that coin. Uh-oh. That's not good. Right, so in a nutshell here, what's happened is that we have lost one of our DC rails on the power supply. Well, we saw everything was working on here, and actually, I'll turn it on. We can still hear the computers coming up. Our AC voltages are good because all of our lights are turning on. But the way this power supply works is that logic power is plus 5 volts for all of this. Lamp power is for the opto-isolation circuits. So anywhere on this that you see a micro switch, or you see the door switch, that has its own separate power supply. And the idea there is that it's a safety mechanism, just so you can protect the electronics within the logic board. The fact that it is going ready to accept the coin means that these boards are fine. Our fault is in the power supply. So we're going to take that over to the bench, and we're going to start troubleshooting it.
Thankfully, Summit was nice enough to make a nice little module for their power supplies. Don't be intimidated by this giant edge connector here. It's a linear power supply. On one side here, we have a heatsink for one regulator, the main transformer, and on the back side, we just have 4 capacitors. There is spots here for soldered components. However, you need to remember that we have the LEDs, we have these 3 switches especially. These are actually logic controls for the CPU card. They're completely passive to the edge connector. So AC power comes in on the top of the edge connector. We have a double height finger on this side and a double height on this. That's just line in neutral. One side goes to the transformer. The other side goes to the power switch on the front. And then it goes into the transformer as well. The transformer steps down the voltage, and now you have AC voltage that you can work with. And this is then where you then have your lamp power and your logic power split off. We have 2 separate bridge rectifier diodes. This is pretty much 4 diodes clustered together into one module and makes AC become DC. The logic side of this is just 5 volts DC, and its regulator hides underneath here. The regulators that are used in this are fairly standard 5-volt variants from Motorola. And if I go back to the desk here again for a moment, there we go. You can, I believe, put 7805s in its place, but those are actually technically less precise than these. I'm not sure if this was just what they had on the shelf or if there is precision needed here within like 2%. These 4 capacitors here are your inputs and outputs for both of these regulators. In fact, the logic requires these 3 caps here, and these are 3300 10 volt, and our lamp is just the one right here. We can test this here on the bench without having to really apply 120 volts to it. But what I'm going to do is I'm going to switch my multimeter on, and we'll go to beep mode. And the first thing we'll do is we'll check to see if our output is shorted. And that isn't shorted. And now we'll check to see if our inputs are shorted. Quite simply, nothing there. Oh. Interesting. Oh, I know what that is. That's the transformer itself. So, yeah. Okay. So, which means on the DC side, are we going to get continuity here? We won't get continuity here. So, okay, that's just the cap charging up there. So, that's why we had our brief continuity. So, there's no short there. On the output side, I know the DC input side is not shorted as well. We can go from ground and verify we have ground to the screw here, which is our 5-volt regulator for the lamps, which doesn't use as much current. As a result, it really doesn't need a heatsink. And now we're able to proceed on to the next tests for giving a little bit of power. We're going to see, it's possible the LED has just simply gone bad. It's possible the regulator has gone bad. It's still possible we have a short in the slot machine. We'll have to poke back on those pins to see if we have something there. Really, otherwise, it could be the transformer that has gone bad. And I find that to be very unlikely because the other voltages out of this transformer are fine. Or it could be the rectifier has gone bad as well. I've seen them go bad. It's not a common occurrence. So I doubt it's that. But to do this, we will take a page out of 8-Bit Guy's book, which itself is like a 6-page manual. And it's very poorly documented. And we'll just ram a voltage in DC back down the output for the regulator. Now, there is a protection diode here. So between the output of that regulator, which is hiding underneath here, and it kind of goes up to this diode, across, and then back over to here. So it won't feed back, not that it's going to matter anyways, because it's basically still going to act like a diode. And I have the current control on my GW model GPS 3030 bench power supply. These great little things, get one now. This is my variance here from 8-Bit Guy. Get an actual variable bench supply. Doesn't need to be anything fancy. The 30 volts, 3 amp little blocks have been on the market now for a considerable number of years. They're cloned to death. They are absolutely fantastic in these applications here because you don't need a ton of current. And they have current control, fine and coarse, and they have voltage control. Very handy. So I'm going to turn my supply on. And I know just from working on these that, and I'll beep this here, so I know my output is way back there. And there's my output right there. Yep. And there's my ground right there. And I can confirm that's my ground. And what I'm looking to do here is I know what my output voltage is. It's going to be 5 volts. So, make sure everything's off. It is. In theory, if there's really no shorts between the regulator and the edge connector here, we should see the LED for lamp power light up a little bit. Doesn't need to be much. I just need to see it light up. See if I can turn the light down here a bit. There we go. And if I just turn up the voltage a little bit. Okay, yep. So we don't have any shorts there. Perfect. So I can confirm that that side is fine. We can also verify that diode, as well as we can also verify the condition of this capacitor. Maybe it is still shorted and we're not aware of it. And we can still verify the regulator by powering that side by going through the input. And I believe, yeah, so that's just tied together. And this is not. Go to ground. Yeah. So what I'll do here, ground on that side, and I'll do positive on that side. And the reason I'm referencing here to the LED is that it's directly tied to the edge connector on the other end. In fact, if I go over here, there you go. So if it lights up, it means that we're seeing a regulated voltage on this. And then we can say, okay, that's not our problem. There we go. And I'm going to apply our voltage. I don't see an increase in current, but I do see the LED light up. And that's at 5 volts. So even with a low voltage, that lit up, and I saw it slowly dim out. So that also means the capacitor is holding a charge. So for these purposes, I will say that it's not the regulator, it's not the cap, it's okay. It's entirely possible that we have a short in the slot machine, because these do have short and overload protection. They will just simply shut themselves down. So let's just go quickly check the output of the regulator. And this is where things get fun. Before going into the regulator, the bridge rectifier can also supply a voltage out through the edge connector of a higher voltage. I'm assuming it's like 12 volts DC or 16 volts DC. I have to double check on the schematic, but we'll take a look at this first to see if there's any shorts. Okay, and on a quick inspection here, we are probing the output pins of the power supply. Everything is in the system as it should be. We don't have a short there. That's good. And if I test here from the accessory plug, which is designed for customer supplied equipment and as a result needs all the voltages, the unregulated input side of the circuit also does not have any shorts within the cabinet. Okay, well this narrows things down a little bit. We've confirmed that a DC voltage unregulated going into the regulator is regulated and is enough to light the LED on the end. We've confirmed there's no shorts on the input side of the regulator, so between the bridge rectifier and the regulator, and we've confirmed there are no shorts from the output of the regulator to anywhere in the slot machine. So that limits us again down to either the bridge rectifier is bad or the transformer is bad. I still find that very difficult to believe. Unfortunately, there are no schematics for this available. In fact, really, there's just like a simple block diagram of how everything works. There's the power supply. There's our +5 to all logic. And then there's this +5 to lamp, and like it says, isolation for static sensitive inputs, and that is our fault. Like it's not overly complicated. We're going to try something here. I don't have a spare bridge rectifier I can drop in here, but since we know that the other bridge rectifier is good because our logic power comes up, if I'm correct and the bridge rectifier is bad, we'll switch those two over, we'll lose our logic power, but our lamp power will come up. Slot machine won't work, but if the lamp power comes on, okay, just get another bridge rectifier. And for that, I will have to now desolder them. Actually, before we desolder them, we will do the competent thing, and I will mark which bridge rectifier I suspect is bad. And now we can remove both and switch them around. Or in fact, I only have to put one back in. That might come out. This one's loose. Yeah, that one just popped out. This one is not loose, so which one do I gotta wiggle here? There we go. You know, since they're out, I just want to quickly see with a diode test what one compares to for the other. Okay. Huh. Okay. Uh-huh. All right. That's interesting. And that's supposedly our bad one. and immediately. This one tests for a diode. This one does not. I think that's the smoking gun right there, but we'll test it anyways. So I'm going to put that one back in there. I'm just going to quickly solder that back on. Yeah. Okay. Gonna have to do this one-handed. Fun. Get a glob of solder onto the iron, and then just a glob there. And now that's in place for me to solder it in. Now, because this is two independent 5-volt circuits, and this isn't an application where anything will be damaged if we're missing one voltage rail, because all we're doing is just operating the isolated circuit. Technically, right now, none of our logic will come up. This is a safe way to do it. So let's go throw the module back in and see if our lamp power comes back on.
All right. I'm going to turn off my light here so I can see. We are on. I'll hit the switch here, and we have lamp power now, and logic power is out. So, yeah, that is our smoking gun. One bad bridge rectifier. And just because someone's going to say, well, you only soldered one bridge rectifier back in, maybe that's the reason why the other one doesn't come up here. Well, I've put the other one that we now suspect is bad back in where logic power goes. You might just barely make out that it's marked right there with a dot. That is our supposedly bad one. So I will just again put that in, on, and we still don't have logic power. So that is by all means guaranteed the smoking gun. We've narrowed it down to a bad bridge rectifier.
So normally I do not see bridge rectifiers die unless they have had something catastrophic happen upstream which has made them short out, or a horrible spike. And in this situation here, we've tested, there's no shorts, there's nothing on here to imply that there could have been a spike. We know the cap is okay. I would say this has just simply died a natural death. In fact, you're not going to make this out on the camera, but I can. This here is actually a repair sticker from the last time it was repaired, or one of the last times it was repaired. And this says June 16th, 1981. So, lasting 40 years before having to be repaired again, I'm satisfied with that. I can give it a new bridge rectifier for that. I'll have to go hunt one down because I do not seem to have one available right now in the diode bin. So hang on a little bit here, and hopefully when I get back to you, I will have a replacement one and we can test it again. There we go. We have one replacement bridge rectifier. As it turns out, this was a lot more difficult to get because I'm used to like 4 amps, 8 amps, 10 amps, 15 amps. They're huge bridge rectifiers. This one here is 1.5 amps, so it's very, very tiny. This one here is designed to operate at a max current without a heat sink of 2 amps, which is just enough. And, yep, all I have to do is I'm just going to drop it in. And we're going to very quickly put 4 drops of solder in here. Turn the iron off. Clip our leads. And that's it. We should be ready to go. So let's head back over to the slot machine.
Alright. So if I can just one-handed get this in here. I totally missed it. There we go. Goes in. Switch is on. And if I've got that bridge rectifier in backwards, we'll see a bit of a... I don't want to think about it. Okay, ready. 3, 2, 1. There we go. Okay, now here comes the big test. If I flick this, we should hear the handle release. And we got it. All good. And that was it. Just a simple bridge rectifier problem on this little power supply. We're back up and running again. Hope you enjoyed watching this repair video, and until next time, have a good one.